Good evening. I'm Spot On Weather meteorologist Matthew Euler, and welcome to video number 4 of the summer weather video training series. And we have a very interesting topic tonight. We're going to delve into the world of jet streams, those rivers of air. These rivers of air have a very meaningful impact on the weather we experience, believe it or not, at the ground. So we're going to get into the definition of the jet stream. We're going to talk about the different types of jet streams and some special cases which can result in some extreme storm development. So let's first talk about the definition of the jet streams. What is a jet stream in general? It's a relatively strong, quasi-horizontal wind that's concentrated within a narrow air current in the upper troposphere. If you remember the lesson on the layers of the atmosphere, we talked about the troposphere being that layer closest to the Earth's surface where we live. We live in the lower part of the troposphere. The troposphere is where all the weather occurs, and that's the importance of the troposphere. But high up, between 30 and 40,000 feet in the upper troposphere, resides these upper rivers of air known as jet streams. Now, technically, from a meteorology standpoint, we will classify a jet stream in those upper levels of the troposphere when those wind speeds reach 50 knots, or typically greater than 50 knots. And the history, what's interesting is the history of the jet stream. There was a lot of research done back in the 1920s by a Japanese meteorologist. He was doing a lot of balloon launches, and he noticed very strong winds in the upper levels of the troposphere when he launched these balloons. But in reality, we really didn't care as much about that discovery until we got to World War II. And during World War II, we had our American B-29 bomber pilots. They noticed that it took longer and required more fuel when they flew from the Hawaii area or from the west coast of the United States, when they flew from east to west, toward the west, towards Japan. And they noticed they experienced a lot of stronger headwinds, sometimes on the order of 230 miles per hour. And they always wondered, well, why, when I travel from Japan, from west to east, why do I get there quicker, and why does it require less fuel? And so that really cemented the concept of jet streams during World War II. Now, what are the causes of jet streams? As I mentioned before in the previous training videos to this point, I mentioned the importance of the sun. And the sun is really the main element that gets everything going in the atmosphere. It heats the surfaces, and surfaces heat differently. Water and land do not heat at the same rates. Various surfaces, snow cover, there's a high reflectivity with that. So everything really ties and goes back to the sun. That's our most important star, and that really gets things going in the atmosphere, especially when we talk about temperature differences. We talk about these large horizontal temperature contrast or differences, and those are associated with what's known as a large thermal wind vector, thermal being heat. I won't really, for the sake of simplicity, I won't really get too in-depth on the thermal wind vector, but just realize that we have large horizontal changes in temperature. That really energizes the upper rivers of air known as the jet stream. And so during the winter time, we have a very strong temperature contrast over horizontal distances. We might have temperature drops on the order of 20 to 30 to even 40 degrees Fahrenheit over a distance of 50 to 100 miles. So we can have very sharp contrast during the winter time, and that energizes and causes these jet streams to form. Now, the jet axis itself, and I'll go into the parts of the jet stream, but the jet axis is near or at the tropopause. because, and this is the upper troposphere. Remember that the tropopause is that layer that divides the troposphere and the stratosphere. It's a transition layer. So that jet axis resides near or at the tropopause because this is where what's known as the height gradient force is at a maximum. And also I want you to remember when we talk about upper level winds, we talk about something known as a height gradient force. It's abbreviated HGF. And all it means is that we have a large height difference, very high heights, narrowing and going down to very low heights over a shorter distance. And that will energize the jet and make the winds blow quicker along that jet axis. So above and below the tropopause, we have a slope of a constant pressure surface and it weakens. And we will also talk about another cause of the jet stream. And this mainly applies to the special jet stream known as a subtropical jet stream. That's known as the conservation of angular momentum. And that happens to deal with, we haven't covered it, but it happens to deal with what's known as a three-cell theory, in which there's a cell which runs from 0 degrees latitude, the equator, to 30 degrees north and south latitude. That's known as the Hadley cell. So that conservation of angular momentum is another cause of that special jet stream known as the subtropical jet stream. We're going to get into that a little bit later. Right, but first we need to figure out, okay, where do these jet streams typically form? When we look at the upper level charts, if you notice on the vertical axis, so in the vertical on both sides on this chart, I have it labeled surface, SFC, 10K is 10,000 feet, 20K, 20,000 feet, 30K, 30,000 feet, and 40K, 40,000 feet. And you'll notice on this particular image, in this case, we have warmer air. If you look on the horizontal axis now, to the left, I'm going to the north. To the right, I'm going to the south. Notice my temperatures. The temperatures are in 10 degrees Celsius increments, and they're the red dashed line on this image. So you notice how, I mentioned this in the previous training video, the tropopause height will vary based on what latitude you're at. So the further south you go, closer to the equator, the more direct the solar radiation, the greater the heating, and as a result, when the atmosphere is heated, it wants to expand. So you see the blue marking here, the blue solid line at the top of the diagram, TROP. That's the height of the tropopause. So if I go to the right, I'm looking at the bottom there, the horizontal line, to the right is the warm air. To the right, I'm going to the south in the northern hemisphere, closer to the equator. My red dashed lines, my temperature lines, they actually get higher and slope upward with height. My tropopause may be up over 40K or 40,000 feet in height, closer to the equator. Now, if I get towards the mid-latitudes, or around 30 degrees, let's just use 30 degrees north as an example. My tropopause is going to get closer to the Earth's surface, because as I move poleward, my temperatures are getting colder. As they get colder, the atmosphere is much more compact, and therefore my tropopause height, as I go further to the north, look on the left there, at the bottom on the left, I have an arrow with north going to the left. That tropopause height comes down drastically, as well as the red dashed lines, those isotherms or lines of equal temperature, those slope downward as well with the height of the tropopause. And where the jet stream forms, it's going to form where the tropopause has an abrupt change in height between latitudes, typically at 30 degrees and 60 degrees. That's where the core of your jet's going to form. And in that little area I have here labeled jet, that little opening or gap between the higher tropopause in lower latitudes and the lower tropopause to the left at the higher latitudes, that little break is known as a tropopause fold. So you see that yellow representation of my jet. It will form at the overlapping of tropopause folds. Right, so what are the characteristics of jet streams in general? Again, as I mentioned, the tropopause heights are going to change abruptly. All right, so you see again the solid blue line in this image, how we go from warmer air on the right, colder air on the left, and look how much lower a tropopause height varies abruptly. It drops abruptly. It gets lower on the left because we're in colder air. The atmosphere is much more compact. right? The tropopause tends to be discontinuous. In other words, I have these overlapping folds in two specific locations. When I say discontinuous, that would be in the subtropics around 30 degrees latitude. That usually occurs over the subtropical ridges or subtropical high pressure systems, as well as in the mid-latitudes around 60 degrees latitude near the polar front. So those are my two locations where I have these jet cores forming. And I'm going to get into that here more in a minute. Now the location of the jet stream, it's found in these discontinuous areas known as the tropopause folds. Some may term it tropopause breaks, and generally they occur between what's known as tropopause leaves. I'm not going to get too technical here. I'm trying to keep this very general for the audience out there so you can really get a basic understanding. But in general, the jet stream forms above the significant temperature or potential temperature gradients of the troposphere. So the greater the temperature difference over a shorter distance, the more energy we have, the greater the potential for acceleration of air within that jet stream. Now, we need to talk a little bit about these tropopause leaves. There's three major tropopause leaves, all right? And I'm going to show you the diagram after I just briefly go through it here, the main points of each leaf. The polar leaf is lower, okay? It's lower because as I get closer to the poles, my tropopause gets much closer to the Earth's surface due to the coldest air. So it's lower and therefore warmer than other leaves. And the only reason it's warmer is because it's at lower altitudes or lower elevations. Polar leaf is generally located poleward of 60 degrees latitude, and it may extend farther equatorward within major troughs in the jet stream. So when we have these big U-shaped dips in the jet stream, that polar leaf may actually extend further equatorward within those major troughs. The middle latitude leaf is generally located between 30 and 60 degrees latitude in both hemispheres, and it may not extend at all in regions where the polar front jet, and I say polar front jet, that's a special type of jet, and we'll get into that here more in a moment. That's abbreviated PFJ, and subtropical jet, STJ, when they merge, the mid-latitude leaf may not extend at all in regions where those two jets merge. And I'll get more into merging at the end of the lesson. And then finally, we have the third leaf, which is known as a tropical leaf, and it's higher. Why is a tropical leaf higher? Because the air is greatly heated at the equatorial areas, the tropics. The atmosphere wants to expand once again, and that tropopause height is much higher. So we have higher, but why is it colder? Because as you go higher in the atmosphere, the temperatures do drop. All right, so it's higher and colder than the other leaves, and it's generally located in that tropical belt, equatorward of 30 degrees latitude, and it may extend farther poleward. So this tropical leaf may extend farther poleward within major ridges in the jet stream. And I'll show you what a ridge looks like here a little bit later on as well. All right, so graphically, this image, by the way, courtesy of NOAA. Generally, I've got them labeled on here, okay? The image, so if you look at the very bottom of this graphic, you'll see equator, 30 degrees north, 60 degrees north, and then on the far left on the bottom there, horizontally, is the North Pole. And you'll notice we have the subtropical jet labeled, and the subtropical jet, that forms in between the tropical leaf and the mid-latitude leaf. So tropical jet typically forms around 30 degrees latitude. The polar front jet typically forms right there between about 60 degrees north latitude, basically in the tropopause fold between the mid-latitude leaf and the polar leaf. And so each one of these red lines represents a leaf. The image on the upper right, I label tropical leaf. So you know how the tropical leaf is in the tropics. The height of the tropopause, that red line, is much higher in the tropical areas because it's much warmer. And notice how the slope of your leaves, the slope of the leaves gets closer to the Earth's surface. It's lowest at the North Pole. And these jet streams, they form in those folds. Generally, we have subtropical jet at 30 degrees latitude and the polar front jet at 60 degrees latitude. And you can see these circulation cells. We have the Hadley cell on the far right. That generally forms between the equator and 30 degrees latitude. The Ferrel cell, or what's known as the mid-latitude cell, forms between 30 and 60 degrees latitude, and then the polar cell occurs from 60 to 90 degrees latitude. That would be the North Pole. So again, the important points to take away from this diagram, showing you the three leaves. Tropical leaf, the highest, the coldest. Mid-latitude leaf is kind of like the in-between leaf, where the tropopause is starting to slope closer to the Earth's surface because we're getting into colder air. The polar front jet forms there between the mid-latitude and the polar leaf. Subtropical jet between the tropical leaf and the mid-latitude leaf. Right. So there are two major types of tropopause folds. Generally, the tropopause folds associated with the polar front jet stream. These may extend deep into the troposphere along the polar front. And they're indicated by tight vertical packing of what's known as isotropes, which extend from the stratosphere. Now, the stratosphere is the second layer of the atmosphere towards the Earth's surface, towards the ground. When we have tight isotrope packing in the vertical, that indicates very stable air associated with the polar frontal layer. We won't get too in-depth on this for sake of simplicity. Just realize basically what I went over in the last slide, where these particular jet streams are located in the tropopause folds. Now, there is significant intrusion of stratospheric air. So air from the stratosphere, which is that second layer of the atmosphere, deep into the troposphere, that can occur in some of the polar front jet stream tropopause folds. Now, there's some important things we need to talk about in the training today. First thing is ageostrophic motion. Okay, and I'm going to show you a breakdown of what's known as a jet streak. And this is an accelerated special area within the jet core that plays a significant role in the development of rising and sinking air in the vertical in the atmosphere. But just realize ageostrophic. Ageostrophic means things are out of balance. That's all you need to remember. The forces of motion that are involved in upper level winds are not equal and opposite to each other. There's a temporary favoring of one of the forces is stronger than the other. So we have this ageostrophic motion where things are not in balance in two specific areas. When we talk about these accelerated regions of wind within the jet stream core, they're known as jet maxes or jet streaks. So we have ageostrophic motion within the entrance region of the jet streak. It drives a direct circulation. Upper tropospheric convergence. When I say convergence, I'm talking about air that's coming together, and subsidence on the cyclonic shear side of the jet will fold the tropopause. Okay? So ageostrophic again means things are out of balance. The forces of motion are not equal and opposite to each other. And I'm going to move on. We have tropopause folds associated with the subtropical jet, and these rarely extend downward below 500 millibars or 18,000 feet. And I really won't get too in-depth on this with the overall specifics of the tropopause folds and the packing of what's known as isotropes. We're going to keep moving forward here. This is a great summary diagram right here that shows tropopause folding and associated direct circulations. Again, PFJ stands for polar front jet stream. STJ stands for subtropical jet stream. I basically have a slice of the globe or the Earth, and I have latitudes labeled 30 north, 30 N, 60 degrees north latitude. Notice the polar leaf, it basically extends from the North Pole 90 north down to 60 north, and within the break or the folds between the mid-latitude leaf and the polar leaf, we have the polar front jet. Between the tropical leaf and the mid-latitude leaf, we have the core of the subtropical jet around 30 degrees latitude. And I kind of summarize it here at the bottom with that information. But just realize that we have a polar front jet, we have a subtropical jet, STJ, we have the various leaves, which we already covered, and we have these discontinuous breaks known as tropopause folds, and that's where those cores of those two specific jet streams form. Now, we can actually see it when the tropopause folds occur because we have a tool. We have a water vapor satellite image, which is a very nice tool. And when we look at a water vapor image, we're looking at the moisture, the atmospheric moisture and the middle layers of the atmosphere. And we can identify this. I'll show you what it looks like here in a minute. But on this water vapor satellite imagery, you'll see elongated or stretched out dark areas which indicate drier air. And they're typically formed on the cyclonic shear side of the polar front jet and subtropical jet. What is the cyclonic shear side? That is always on the colder, if we're in the northern hemisphere, that'd be on the colder side to the north of the main polar front and subtropical jet stream axis. Here is what it looks like, a water vapor satellite imagery. This is displaying that tropopause folding, and we're looking at tropopause folding associated with the polar front jet. This is the infrared, emphasized the dry aspect. So the darker areas on this water vapor imagery, this image was taken on 4 February of 2003. It's a GOES-8 image from the University of Wisconsin-Madison. The darker areas on here generally indicate tropopause folding, where the atmosphere is really dry. The yellow dashed line represents the jet axis, the polar front jet axis, the main core of the polar front jet. To the north of that axis is where you have the colder polar air, and to the south of that yellow dashed line, south of that polar front jet axis, you have the warm tropical air. So let's take a look now and move on here to the typical dimensions of a jet stream. Generally, jet streams are thousands of kilometers long. They're hundreds of kilometers wide, and they're several kilometers in depth, or if I were to look in the vertical. Length, thousands of kilometers again, width, hundreds of kilometers, and depth, several kilometers in depth. So these jet streams can extend all the way across the globe. Again, very important because they play a significant role when we talk about the accelerated regions within the jet stream axis, those jet streaks. They can lead to explosive storm development. In addition, they control the rising and the sinking air motion in the atmosphere. Think of the atmosphere as a three-dimensional fluid. In addition, jet streams steer those baroclinic, those transitory lows and high pressure systems that we went over in the last video 3, the last training session. All right, so the physical structure of the jet stream and its relationship to the thermal structure of the atmosphere. So these are the different parts. If we were to dissect, like a doctor dissects a human body in the different parts, the jet streams are broken down. If we break it down into pieces or parts, we start with the jet core. And the jet core is a region of relatively uniform wind speeds in the interior of the jet stream. So the wind speeds are fairly constant, very uniform. Due to the uniformity of these wind speeds, we usually don't have much shear if you're directly within the jet stream core. All right, now wind shear, it can be caused by two different things in the atmosphere. When we talk about upper level winds, wind shear can be caused by changes in wind speed across distances, horizontal distances. It can also be caused by wind direction changes, directional shear. Now, moving on to the jet axis. This is the axis of maximum wind speeds in the jet axis, and it runs through the center of the jet core. Right through the center of the jet stream is where you find the jet axis. And then finally, we need to really get into these very significant features within the jet stream axis, and these are known as jet maximum or jet streaks. I'll call them jet streaks for simplicity of the training. These are the areas of ageostrophic flow where the forces get out of balance, and I'm going to break that down here in a moment, how things get out of balance within these jet streaks. These are intermittent regions of strongest wind speeds within the jet. In this below image, I'm showing an anticyclonically curved jet streak, kind of like an upside down U pattern, and then I'm showing this big dip in the jet stream, cyclonically curved jet streak. The jet streaks in this particular image are indicated by the highest wind speeds. So if you look at that dull blue there, where the arrows are pointing to for both jet streaks, both curved jet streaks, the wind speeds there are between 130 and 150 knots. So we have some very strong wind speeds. So you notice these are intermittent regions too. The jet streaks do not go through the entire jet axis. They're little segmented areas of of higher wind speeds. And the isotax, iso literally means equal, and tax means wind speed. So if I say isotax, I mean areas that have equal wind speed. These define the jet max, that do define the jet max or jet streaks, are somewhat elliptically shaped, both horizontally and vertically. So elliptical, I want you to think of, and I'll show you an example of an elliptical shape here in a minute, but I really want to tie it in with something really familiar. Think about a football. So now, how does this ageostrophic motion occur at jet streaks? This is really, really interesting. Okay, I have this diagram here labeled. Now, the center of it with the circular, the elliptical shape, that indicates the jet streak itself. To the north, if I was going to the left or to the north, I have lower upper level heights. If I go to the right or to the south of this jet axis, I have higher heights. I have points labeled 1, 2, 3, 4, 5 along the main jet axis. Okay. The solid lines represent what are known as height contours, lines of equal geopotential height. All right, so we have two forces that we're really, really concerned about when we talk about airflow in the upper levels of the atmosphere through these jet streaks. The first force is labeled PGF, all right, and usually in the upper levels we like to talk more of HGF or height gradient force, but again, for sake of simplicity, we'll call it pressure gradient force PGF on this diagram. We also have what's known as the Coriolis force that's involved as this air parcel accelerates through this jet streak or area of accelerated jet speeds. So in all cases in the atmosphere, everything, when we talk about pressure gradient force particularly, pressure gradient force always is directed from higher toward lower. If you're on the surface of the Earth, higher towards lower surface pressure, from high to low pressure. If we're in the upper levels of the atmosphere, pressure gradient force is always directed from higher heights toward lower heights. Coriolis force is always going to act to the right. In the northern hemisphere, it's going to act to the right of air motion. Okay, so with ageostrophic motion, I want to introduce the concept of pressure gradient force and Coriolis force. Those are the two forces that we need to talk about. So at point 1, I have this little tiny air parcel, and it's moving along this main jet core or jet axis, and my higher heights are to the basically below this jet axis. My lower heights are up above to the left. So initially the air parcel, the pressure gradient force, and the Coriolis force are going to act equal and opposite in direction. Pressure gradient force directed to the left toward lower heights. Coriolis force is directed to the right of the air parcel's motion, which is basically from left to right on this image. So at point 1, everything is good. The pressure gradient force and the Coriolis force are equal and opposite to each other. We have a balance of forces. And the main arrow there pointing from point 1 to point 2 is showing the direction of travel of the air parcel. It's showing that the winds in the air parcel are in perfect balance. As I get to point 2, I move into what is known as the jet streak entrance region. And in the entrance region, the air parcel is suddenly accelerated. Suddenly, these winds really pick up quickly. The air parcel is accelerated, and because of that, the pressure gradient force is actually temporarily stronger than the Coriolis force. So what happens is I have ageostrophic motion right there at point 2 as soon as this air parcel enters the jet streak entrance region. My pressure gradient force is much stronger, directed from higher to lower heights toward the left. And my Coriolis force is a shorter arrow directed toward the right. As a result of this, the majority of my mass is going to be deflected to the left, okay, at point 2. And I'm going to have a removal of mass right there where you see RR, the letters RR, that means right rear. That means right rear quadrant, okay? So all my mass is being removed or taken from the right rear quadrant to the LR, left rear quadrant of the jet streak. So I'm losing mass in the right rear quadrant. I'm gaining mass in the left rear quadrant. Now, as the air parcel moves to point 3, as it moves to point 3, I get right in the center of this accelerated area of higher wind speeds in the jet streak, and my parcel is happy again because the forces are completely balanced again right in the center of the jet streak. The pressure gradient force and the Coriolis force are now at point 3, equal and opposite to each other, right down the dead center of the jet streak. So everything is good again. But as the parcel moves from point 3 to point 4, now we're moving into what's known as the jet streak exit region. And now, because my parcel is moving from a higher wind speed area to a lower wind speed area, the parcel starts to slow down. But the Coriolis force is pushing everything to the right. The Coriolis force is temporarily stronger towards the higher heights from left to right, and my pressure gradient force directed to the left is much weaker temporarily. And as a result, I now have the mass being pushed, excessive mass or addition of mass is being pushed towards the right out of the jet streak exit region. And as a result, I have more mass in what's known as the right front quadrant of the jet streak, and I'm losing mass in the left front quadrant of the jet streak. And then finally, when we get to point 5 on my diagram, the parcel's happy again because the pressure gradient force and the Coriolis force are again equal and opposite to each other. So what does this mean? This means that we typically get rising air motion in the left front and the right rear quadrants of these jet streaks. That's where you're going to find the rising vertical air motion. That's where you're going to find, when you have rising air, you have cooling air, you have clouds, you have precipitation, and most likely rising air will result in lower pressure and storm development. The areas in the right front and the left rear quadrant with the addition of mass in the upper levels of the atmosphere is going to result in sinking air motion, and you're going to typically have high pressure systems and much nicer weather in those two quadrants. Here is a quick summary of everything I just covered. We talk about jet streaks, the entrance region on the left, the exit region on the right. And you see mass is added. Wherever mass is added, the right front quadrant and the left rear quadrant, see where there's sinking air, where the mass is added. You get addition of mass in the upper levels of the atmosphere. It has to go somewhere, so the air sinks. The left front and the right rear quadrant, the mass is removed because of that imbalance of the Coriolis and pressure gradient force. If mass is removed in the upper levels of the atmosphere, you get low-level rising air from the lower troposphere to come in and replace that removal of mass aloft. So you generally have additional mass is equal to sinking air motions, removal of mass is equal to rising air motions, and wherever you see rising air, it's favorable areas for storm development. So jet streaks are very, very important features in the atmosphere. Okay. Again, for the sake of simplicity, I'm going to just completely go over these two slides here. Not really as important. We're going to move into something, we talk about shear and turbulence associated with the jet stream. They're directly related to the strength of the isotact gradient and the stability in the atmosphere. So airline pilots especially, they fly up at 30,000 feet. They're flying in the vicinity of where the jet stream is. There can actually be a special type of turbulence where there's no clouds at all, and this is called clear air turbulence, and it's very dangerous for a pilot because they don't see any kind of indicator of this type of turbulence. Completely clear blue skies, and all of a sudden the plane gets buffeted around a little bit by some turbulence. So you can get a lot of varying wind speeds across this jet core, across the jet stream itself over short distances, great changes in wind speed, and if that happens, you're going to get what's known as turbulence in the atmosphere. Okay. I'm going to move through a little bit more. Okay, we talked about clear turbulence. Additionally, when you have jet streams that are crossing large mountain ranges, such as the Rocky Mountains, this may generate large waves in the atmosphere. And some of these waves may become unstable and break, creating what's known as severe mountain wave turbulence. And there's special type of clouds that form at the mountain, top of the mountain and downwind of it. They're kind of look like spaceships or UFOs. These are known as altocumulus standing lenticular clouds. They really don't move a whole lot, but they indicate extreme turbulence. Pilots definitely want to steer clear of those type of clouds. And that's when you have strong winds that are blowing up against these really tall mountains, and that can induce some turbulence, mountain wave turbulence. Okay, and there it is, the standing lenticular clouds. Mountain waves are often associated with these, and they call them standing because they really don't move a whole lot. Okay. There's also something else that's really interesting, and the timing of this is really coincidental. Just recently in Virginia, there were some images sent out in news media outlets of something known as a Kelvin-Helmholtz cloud. And this is due, these Kelvin-Helmholtz clouds, I'm going to show an image of what it looks like here in a minute. It's a pretty cool looking cloud. It's caused by strong vertical wind shear through the polar front, through higher up and aloft. And it may induce wave breaking and turbulence, similar to waves on an ocean. It looks very much like an ocean wave, except it's a cloud in the atmosphere. Sometimes we refer to these Kelvin-Helmholtz clouds, we refer to them as billow clouds. And they're a really unique type of cloud. Let me show you what it looks like. See the clouds, these images, it almost looks like ocean waves. And they're really cool. They're caused by different layers of the atmosphere having varying wind speeds. So the wind is changing as you go up, up, up. The wind is changing wind speeds drastically. The upper layers are moving at higher wind speeds, forming this wave-like appearance at the top of the clouds. They typically form on windy days, and they indicate unstable atmosphere. And these are very turbulent to aircraft. So again, if you're in a plane and you ever see one of these lines of these Kelvin-Helmholtz or billow clouds, it's definitely something you want to avoid because there's a lot of up and down air motion over a shorter vertical distance. So you definitely want to steer clear of these clouds. All right, now we get to move into actual discussion of jet stream types. We have the polar front jet, which is abbreviated PFJ, and the primary cause of this jet is horizontal temperature differences or contrasts in the troposphere layer. And again, the locations in that tropopause fold, as we already covered, between the polar and mid-latitude tropopause leaves, you have stratospheric air on the cyclonic side of the polar front jet. If we're looking in the northern hemisphere, that means north of the polar front jet. There's stratospheric air. Then we have tropospheric air on the south side of the polar front jet. Now, what's interesting about the polar front jet is it does change or moves with the seasons. In the wintertime, we have much colder air masses that break free from the Arctic and come into the middle latitudes where we live in the United States. And as a result, the polar front jet stream moves much further south, closer to the equator. In the summertime, on the contrary, the temperature contrast is pretty much reduced. You pretty much get the sun to heat most of the continental United States, and so the polar front jet actually moves closer to the poles in the summertime and is usually much weaker. So the height of that polar front jet is also going to vary with the height of the tropopause and will vary from season to season. The seasonal intensity of the jet maximum speeds, again, as I mentioned, we have a weaker wind speeds within the polar front jet axis. They're weaker in the summertime when the temperature contrast is not so great between the latitudes, and it's much stronger in the wintertime where you have a very sharp change in temperatures over a horizontal distance between the latitudes, north and south latitudes. The core height of this jet varies with the tropopause again. Just keep in mind in the summertime you have greater heating of the atmosphere, which the atmosphere then wants to expand. So the height of the tropopause, the height of the polar front jet is going to be higher in the summer as compared to the winter when it's much colder. Here's an example of just showing you some wind barbs, showing you a general trough shape, the polar front jet stream making this dip, this U-shaped pattern that's known as a trough. And rules of thumb, what am I looking for to identify where the polar front jet is? Okay, first thing as a meteorologist, we're going to look for the area that has the strongest, generally from 300 millibars, 30,000 feet, up to 250 millibars, which is about 35,000 feet. We're going to look for, on the upper level charts, the 200, 250, or 300 millibar charts, we're going to look for the tightest packing of the height contours. That's going to be a good indicator of where the polar front jet stream's at. Usually located above the tightest thickness packing. If I were to look at a 1,000 to 500 millibar thickness chart, I would also look for that tightest packing of the thickness lines to identify where that axis of the polar front jet is. So in general, these are good rules of thumb. If you're looking at specific 250 millibar, that's about 35,000 feet, or 300 millibar, 30,000 foot weather charts, upper air weather charts. Just keep this in mind with the polar front jet. It's generally found on the poleward side of the surface polar front. So it's generally found north of that surface polar front. The surface polar front is an area typically where we have storm development around 60 degrees latitude. Okay. You will see these cirrus cloud decks as well, and these cirrus cloud decks will form or persist on the south side of the polar front jet axis. You'll also see a well-defined cloud border. Normally they exist along the jet axis itself. If I were to look at the water vapor imagery, I would find the polar front jet stream axis generally on the north side of the forms that persist, the elongated dark regions. I'm looking for elongated dark regions on the water vapor satellite imagery to identify where my jet axis is, where that jet stream's at. Here's some examples of some charts to show you actual jet stream analysis. The shaded areas represent the areas with the highest wind speeds on the various upper level charts. And then we move into the second type of jet stream, which is just as important, believe it or not, especially in wintertime when we talk about major storm development. This is known as a subtropical jet stream, and it's primarily caused by two factors. One of those is when you get these upper level meeting of air or convergence aloft of air, and that results in sinking air motion. Additionally, you have that upper level convergence, and we'll talk about the angular momentum concept here in a moment. So again, just as a reminder, where does that subtropical jet stream form? It forms basically between the middle latitude leaf on the left, and that other blue line there is your tropical leaf. The tropopause height will vary. You have a subtropical ridge, which typically is situated around 30 degrees latitude. So the subtropical jet is fairly close to where that subtropical ridge or that high pressure develops, actually. So the location of the subtropical jet stream, this one is really important as far as bringing moisture in to the lower 48 in the United States. But the location of the subtropical jet is typically between 15 degrees and 35 degrees latitude. And climatologically in the northern hemisphere, the subtropical jet is closest to the equator over the eastern ocean basins, and it's farthest from the equator or furthest to the north over the east coast of North America and Asia. But the actual position is going to vary and show large fluctuations. The tropical East Pacific and tropical East Atlantic ocean regions are favored origin regions of the subtropical jet, and I'm going to show you an example of this in a moment, but there's a special type of feature on satellite imagery that's known as tropical plumes, and these are extensive cloud shields that are associated with vigorous subtropical jet streams. And tropical plumes generally originate in the deep tropics between 5 degrees and 15 degrees north latitude, and they extend northeastward into the middle latitudes. Let me show you an example of a tropical plume. All right, so again, for jet stream identification, what I'm looking for are the darker areas on water vapor imagery. I'm showing you a water vapor image here. The lighter colors represent where there's moisture. The darker colors indicate where the air is dry. And typically your jet stream axis forms in these darker locations. But you do notice the leading edge of this subtropical jet just to the east of Hawaiian Islands, on this particular example, there is a plume of moisture represented by that brighter white color where the arrow's pointed to, and that is on the very edge of the subtropical jet. So sometimes you can use this little plume that originates from 5 to 15 degrees north latitude and you can use this plume as an identifier to locate the subtropical jet stream. Now, the subtropical jet stream, when we talk about it, we have to talk about a concept known as the conservation of angular momentum. This is a factor in accelerating the subtropical jet stream as it extends from southwest to northeast. As it gets closer to the polar areas, the velocity changes. Basically, just a quick crash course, since I won't get too technical on it, but angular momentum is equal to mvr. That's the formula for it. M is equal to the mass, V, the capital V is the velocity, and the smaller lowercase r represents the radius of Earth's curvature. And just think about this. The Earth is much wider at lower latitudes at the equator than it is the polar areas, so the radius of curvature will get less and less as you go from the equator towards the poles. And as a result, the Earth's radius decreases as you move closer to the poles, and this is going to increase the velocity of the air parcels in order to keep the angular momentum constant. Okay, so if I decrease the radius, my velocity increases. It's an inverse relationship. And then the Coriolis force, we also need to talk about that when we talk about the upper level winds associated with subtropical jet. That's really just a manifestation of the conservation of angular momentum. It causes a recurvature because as velocity and our latitude increases, the Coriolis force increases and that turns the jet stream more anticyclonically to the right. Keep in mind that the seasonal intensity of the subtropical jet stream is strongest in the wintertime, similar to the polar front jet. It's strongest in wintertime. Tropical plumes nearly always occur during the winter, and it's usually weakest during the hurricane season of the subtropical jet. But in special cases known as El Nino conditions, the subtropical jet is typically stronger than normal, and that plays a major role in the hurricane season activity and intensity. When you have a stronger subtropical jet stream during El Nino conditions, that tends to rip apart thunderstorms as they try to form in the tropics, and it tends to limit or lower the number of hurricanes in a typical North Atlantic hurricane season. So when we look at El Nino, we look at a lower number typically of hurricanes across the North Atlantic. General core height of the subtropical jet, remember it resides between the mid-latitude and tropical leaves. It's approximately at 250 millibars. It's about 35,000 feet above the ground, all the way up would go all the way up to 50,000 feet above the ground. So the subtropical jet is much higher in altitude or elevation as compared to the polar front jet, which we would expect because we're at lower latitudes where the air is warmer, the atmosphere wants to expand. A feature that's really useful in identifying the location of a subtropical jet is what's known as jet cirrus. They're commonly found on the warm air tropical leaf side of the axis, and these jet cirrus typically show up as transverse bands for subtropical jets. Let's take a look at an example of a transverse band. So on the upper left-hand, kind of like the left-hand portion of this satellite image, this is an infrared satellite image. The coldest cloud tops are indicated by the lighter white colors. The gray colors in the upper left-hand portion of the image are lower clouds. We have the Hawaiian Islands off to the northwest of these clouds. Generally, the subtropical jet, these transverse bands or areas of cirrus clouds are going to form perpendicular to the subtropical jet axis. So if I were to draw the subtropical jet, I would draw it right through these transverse bands. You can see how they're oriented perpendicular to the subtropical jet stream wind flow. So if you see these high-level cirrus clouds between 15 degrees and 35 degrees latitude, that generally is a good indicator that we have a subtropical jet stream in the area. All right, and the last thing I want to talk about for the training on jet streams is what happens when we get the jet streaks, those areas of accelerated wind velocities within the jet. What happens when they interact with each other? All right, we can get two situations here. We can get it when there's interaction with the polar front jet, PFJ, where you get the confluence or the merging of the polar front jet and the subtropical jet cores. We get these two jet streaks that merge, It results in favorable conditions for development of extreme turbulence, first of all, because you got extreme fast-moving winds superimposed on top of each other. Turbulence is most severe between the cores. If you were to fly an airplane between the cores, it'd be a very bad place to be because that plane would get buffeted around pretty good. When we have the confluence of the two jet streaks between the polar front jet and subtropical jet, that generally promotes the addition of mass or upper level convergence of air and subsidence or sinking vertical air motion in the atmosphere, which suppresses, inhibits, or prevents, however you want to say it. Storm formation is not happening because you have confluence or coming together, addition of mass in the upper levels of the atmosphere. When you add mass in the upper levels of the atmosphere, it causes sinking air motion, and that usually results in clear skies and high pressure systems and very little in the way of storm development. But if you have difluence of these two jet streaks, say you have a merger of the polar front jet and the subtropical jet, those two jet streaks are on top of each other. If you get them to line up just perfectly, this can result in an increase in upper level divergence, the removal of mass at a much accelerated rate in the upper atmosphere. That is going to cause a much stronger rising air motion. When this happens, it favors the formation of severe thunderstorms, especially in the Gulf of Mexico. And you'll see like a V-notch thunderstorm shape in the Gulf of Mexico. That is a dead giveaway that these two, the polar front jet and subtropical jet, those jet streaks are merging, and we have extreme upper level removal of mass, upper level divergence, and very quickly rising vertical air motion. Thunderstorms are often located just downstream of this jet streak. Satellite imagery shows storm tops exhibiting a characteristic, it's going to look like a wedge shape. Okay, so if you get the favorable areas of the jet streaks to merge between the polar front and subtropical jets, or align over the top of each other, so that'd be the left front quadrant and the right rear quadrant. That's where the air, the mass is removed aloft. That's where you have rising air motion and storm development. If the left front or right rear quadrants for the polar front jet and the subtropical jet merge or align, this is where you can get a case of extreme storms. They're known as bombs, and they form a lot of times in the wintertime off the east coast of the United States. They're due to excessive removal of mass and excessive upper level divergence, and I term it bombogenesis. A bomb, a meteorological bomb, is a storm which has a pressure decreasing of 24 millibars over a 24-hour period. 1 millibar pressure drop per hour over a 24-hour period. That defines what we call a meteorological bomb. In an extremely intense storm system, again, a favorable area for this to occur is along the east coast of the United States. We get some of the biggest winter storms when these two jet streaks, these favorable upper level divergent jet streaks merge. Okay. Here's an example of the two jet streams on a water vapor imagery. The polar front jet stream is going to be positioned above the subtropical jet stream. I got both labeled there. Subtropical jet stream, very common to be blowing from Mexico across the Gulf of Mexico in through Florida. And then the polar front jet stream comes down from the north, from Canada, into the lower 48. Again, using the darker colors on the water vapor imagery, the lack of moisture, to identify where the jet stream axes are for both of these types of jets. All right, that wraps things up for the training on jet streams. I really hope you enjoyed the training. We covered quite a bit tonight. Just realize that jet streams play a significant role. They play a significant role in our weather here at the ground. You know, the atmosphere is not a two-dimensional fluid. It's a three-dimensional fluid. So when you're talking about looking at storm development, areas of whether it be rising air motion with the storm development or sinking air motion with high pressure systems, you have to look at weather charts all the way from the surface, all the way up to the 300 or 200 millibar levels, 30 to 40,000 feet. Everything ties in together in the vertical, three-dimensional fluid. This is a very important diagram we went over with the ageostrophic motion. When ageostrophic meaning out of balance, when pressure gradient force and Coriolis force, they're not in balance with each other. due to these jet streaks or higher wind speeds embedded within the jet core. In the left front, if you were to divide this jet streak up into 4 quadrants, if you were to just put a big plus over the top of it and equally divide it, the left front and the right rear quadrant are favorable for storm development. The right front, abbreviated RF, and the left rear, abbreviated LR, are favorable for high pressure and sinking air motion, nice weather. You know, wherever these jet streaks set up is key to determining your weather. If you have the left front quadrant in the left front quadrant, that's in the jet streak exit region, if you have that over your location, there's a good chance you're going to get a storm to develop over your area. You have to look at other layers of the atmosphere, of course, but generally that promotes upper level divergence and removal of mass aloft. Right. So we talked about characteristics of jet streams as well. We talked about how to identify jet streams. If I were to look at water vapor satellite imagery, I'm looking for the darker areas. We talked about where jet streams generally form. 2 types of jet streams: polar front jet, abbreviated PFJ, subtropical jet, STJ. The polar front jet forms around 60 degrees latitude, and the subtropical jet around 30 degrees latitude. As a tropopause adjusts its height based on location on the Earth, that is going to cause these overlapping tropopause folds, and that's where the jet streams form. We realize the subtropical jet forms between the tropical leaf and the mid-latitude leaf. Subtropical jet forms around 30 degrees latitude in the tropopause fold, and then the polar front jet forms in that tropopause fold or discontinuous area between the mid-latitude leaf and the polar leaf. So there we go. We talked about that, and I really again hope you enjoyed this training on jet streams, upper rivers of air. Very, very, very important elements of the atmosphere, and they really make a big difference in the weather we experience here at the Earth's surface. All right, that wraps things up tonight on the lesson on jet streams, rivers of air. We appreciate you watching. As always, video 4, and we're going to continue to move on with great topics ahead, starting with video 5. So please come back and take a look at what we have to offer, training. Feel free to send in questions if you would like as well. Follow us on Facebook, on Twitter, Instagram, as well as the Spot on Weather YouTube channel. Subscribe to get our latest training videos, as well as our forecasts. Also, we have Spot on Weather on the Weebly. If you look up Spot on Weather Weebly, you'll find us where we post a lot of great weather information, including 7-day forecasts. That is all for tonight. Everybody have a great evening. Take care, everybody. God bless wherever you are. That is all.